So hello and welcome to my presentation on my paper titled On the Use of Mahalanobis Distance for Outer Distribution Detection. So to introduce myself, hello, my name is Harry Anthony and I'm a first year PhD student at the University of Oxford. Previously, I completed a Master's in Physics at Imperial College London, and now I'm studying for a PhD under the supervision of Professor Kamnitsas. My main area of research is on improving outer distribution detection for neural networks for medical image analysis. So, when training a neural network, we've got a set of training images and corresponding labels, which we call the training data. We use this to train a neural network on a task of interest, such as classifying diseases from X-ray scans. Once the model is trained, it can be applied to images without labels during inference. Most of these images will be from the same distribution as the training data, which we call in distribution, or ID. However, the model may encounter images that differ significantly from the training data, which we call outer distribution, or OD. It's been observed that outer distribution inputs can cause the network to give erroneous predictions. So in a clinical setting, we want to detect these and then defer decision-making to a human clinician. Outer distribution detection can be thought of as developing a scoring function, dependent on an input image and a neural network. If we plotted such a function, we would want to see the distribution of OD images, shown in orange, separable from the distribution of ID images, shown in blue. We could then place a threshold given by tau, and say everything below that threshold is outer distribution, and everything above that threshold is in distribution. So outer distribution detection methods can be put into two categories. We've got internal methods, which use the outputs or parameters of the model trained on the task of interest, or external methods, which are external to the model trained on the task of interest, such as the dedicated model just for outer distribution detection. We can then further separate internal methods into two further groups. We've got post hoc methods, which can be applied to a pre-trained model, or ad hoc methods, which will require a specific type of network architecture or for the model to be trained in a certain type of way. So there are several benefits to post hoc methods. They can be applied to pre-trained networks. They're usually not dependent on a type of network architecture, and they're also at a low computational cost. And we're going to talk about one of these post hoc methods today, which we call Mahalanobis Score. Mahalanobis Score is widely used for outer distribution detection. However, its performance varies a lot in the literature. It performs very well in some studies and less well in others. So we want to study the best practices for this method. So let's run through the method then. Here we've got our pre-trained network and we're giving it an unseen input image. We can then extract feature maps at some point in this network, and we use the mean of each of these feature maps to define an embedding vector given by the symbol Z. We can use this to study the latent space of the neural network, and we can see where the training data lies. We can then compare this to where the ID and OD data lies in latent space. We can hypothesize that the ID data will be closer to the training data than the OD data. Therefore, by measuring the distance of an input to the training data in the latent space, we can test for outer distribution inputs. It may be intuitive to use the Euclidean distance as our distance metric. However, the Euclidean distance does not take into account the correlation between variables. So in our example here, we see that it's not able to separate ID and OD inputs. Instead, we use the Mahalanobis distance, which does take into account that correlation. Mahalanobis distance is equivalent to Euclidean distance, apart from we divide by the covariance matrix given by large sigma. It can be thought of as fitting a Gaussian distribution to the training data under a maximum likelihood estimator. However, in reality, the training data will contain several classes, which we expect to occupy different regions in the latent space. So to account for this, we measure the mean and covariance matrix of each class in the training data. We then use this to measure the Mahalanobis distance from an input to each class centroid. And we use the distance to the closest class centroid, which we call the Mahalanobis score, as our OD scoring function. The rationale here is that an OD input will not be near any of the classes in the latent space, so a large Mahalanobis score indicates an OD input. So to study this method, we trained a ResNet 18 model on chest X-ray images from the CheckSpurt dataset to classify between images with cardiomegaly or pneumothorax. We trained on 90% of this data and held out 10% as our ID test cases. To create an OD test case, we then added a synthetic grey square to each of these held out ID images. So, firstly, we looked at the case where the grey square took up 10% of the pixels of the image. We extracted embeddings after a module in the network and used Mahalanobis Score as our OD scoring function, evaluating the performance using the area under the ROT curve. We then repeated this for all the modules in ResNet 18. Looking at the results, we see the pattern that the detectability of the grey square reduces throughout the depth of the network, where here the grey dotted lines represent downsample operations. We then repeated this for squares of size 7.5% and squares of size 5%. Here we see, maybe intuitively, that smaller artifacts are less detectable throughout the depth of the network. Moreover, if we zoom in, we see the pattern that the AUC typically improves after a ReLU operation, highlighted in green, compared to its preceding convolution, which is the red circle, or batch norm, which is the blue square operations. The most common implementation of Mahalanobis Score is to extract embeddings from the last in layer of the network. However, when looking at our results, we see that applying Mahalanobis Score on the last in layer actually results in one of the worst possible AUC scores in the whole of the network, which I'll repeat is the most common implementation of this method. We think that the poor results on the last in layer may be diverting the community's attention away from the potential of Mahalanobis Score. So we then repeated our experiments, but this time using a white ring artifact. And here are the results. So the white ring artifact is shown in orange, and the square results are shown in purple. Here we see that the square is most detectable in the early layers of the network, whereas the ring is most detectable in the later layers of the network. We found this result really interesting, that different artifacts have completely different trends, despite the fact this is on the same pre-trained networks. From this result, we can see that there's no single layer which can optimally detect both of these artifacts. Maybe trying to find a single module in the network which can optimally detect all artifacts might be a bit misguided. So another common implementation of Mahalanobis Score is to collect distances after residual blocks in the network and then weight them together to get one single score to use for outer distribution detection. The distances are weighted together using coefficients alpha, which are usually calculated using logistic regression on an external OD dataset. When applying this method to our results, we can see the layers for weighted combinations shown in blue, and the ideal weightings for each artifact are then shown on the right. Here we see that ideal weighting for one artifact actually causes a degradation of performance for another, i.e., there's no single ideal weighting for both artifacts. As the idea of knowing what future artifacts will be before we've seen them is quite misguided because OD artifacts are going to vary greatly and they're very inhomogeneous, we suggest here that the idea of finding an optimal weighting is probably not the correct way of applying this method. So here are some of the key takeaways from our synthetic artifact experiments. We saw that the application on the last in layer can be very suboptimal. The performance usually improves after an activation function, and we saw that different OD artifacts are optimally detectable at different depths of the network. This last point motivates us to think that maybe we need to use multiple OD detectors at different depths of the network to detect different types of OD patterns. To investigate this, we created a method which uses multiple detectors, which we're going to call multi-branch Mahalanobis. How this works is we separate the network into parts, divided by downsample operations. We call each part a branch. We then collect the distances after the modules in the branch, and then weight them together to get a single score. The OD scoring function is then a sum of the standardized distances in the branch, using the mean and standard deviation of the distances from the training data in order to prevent the distance from one single module dominating. We then repeat this for the following branches of the network, such that each acts as its own OD detector, allowing us to have multiple detectors throughout the depth of the network. Moreover, we want to validate our findings on a real-world OD task. However, most OD medical image tasks have heterogeneous OD artifacts, which complicates our analysis on OD patterns. Therefore, I'm happy to say that we've created our very own OD evaluation benchmark. We manually annotated approximately half of the Checkspert dataset, which is around 100,000 annotations, to label if an image contained no support device, which we use as our training data, or if it contained a pacemaker device, which is a visually distinct artifact, and we can use this as our outer distribution test set. As a contribution of this work, we're making these labels publicly available, and I hope this is going to be useful for the community for assessing OD detection methods on a real-world OD task. So we use these manual annotations in the following way. First, we train a ResNet 18 to classify between images with pleural effusion or without pleural effusion, where all of these images have no support devices. We use 5-fold cross-validation to create our ID test set, and then our OD test set is images with pacemaker devices. Our second OD task, we train a model on the same pleural effusion task, but only using scans of male patients with no support devices. We again use 5-fold cross-validation for our ID test cases, and then we use female patients with no support devices as our outer distribution test set. So firstly, we looked at the AUC for Mahalanobis score over the modules ResNet 18, similar to what we did with our synthetic tasks. So here are the results for our unseen sex task across the modules of ResNet 18. We see here that it's most detectable in the middle of the network. And here we've highlighted the branches we're using for multi-branch Mahalanobis with the grey brackets. Now let's look at the unseen pacemaker task over ResNet 18. And we see that this pattern is most detectable at the end of the network in branch 4. Now here we validate our findings we saw on the synthetic artifacts, that different types of OD patterns are optimally detectable at different depths of the network. Now we can compare the results on the pacemaker task to our other post-hoc OD detection benchmarks. I won't go through each method individually due to time constraints, but here we have the baseline max class probability, which does not perform well at only 58%. We see similar performance for Monte Carlo dropout and for deep ensembles, where for the latter we use 3 Cs per k-fold. We do see a notable improvement with ODIN. However, those who are familiar with this method know that it has 2 hyperparameters which need to be optimized on an external OD dataset to improve its performance. However, in real-world deployment, it's impossible to configure these for an unseen OD task, so we're unlikely to get the full potential of this method during deployment. So we're going to mark this method to highlight this. Now let's look at Mahalanobis score applied on the last in layer of the network. We see that this performs very poorly. It actually performs worse than the baseline maximum class probability. And I'm going to say it again, this is the most common implementation of this method. And it's a shame because we're missing out on a lot of potential. Compare this to Mahalanobis score on the best layer of the network. We get a huge improvement, 75%. However, again, it's impossible to know where the best layer to apply this method is for an unseen OD task. So this full potential is not going to be achievable. However, if we look at the weighted combination, which we talked about earlier, and we're using an equal weighting here from our discussion about weighting being a bit misguided, we do get an improvement at 64.5%. And moreover, one of my contributions is to say, let's do this weighted combination, but without the last in layer. We get a further improvement at 71.4%. Now let's compare this to our multi-branch Mahalanobis method. Here we've plotted the AUC for each branch in the network, and we see that the last branch performs very well. It actually performs better than the best single layer in the network. This result highlights the utility of aggregating distances together to get one single score. So this is good, but we can do even better than this. Remember before I mentioned that AUC typically improves after a ReLU operation? Well, if we use multi-branch Mahalanobis just after ReLU operations, we get a further improvement in the AUC. However, we can do even better than this by using a method called fast gradient sign method. How this works is we backpropagate the Mahalanobis distance as a loss, and we use this to calculate perturbations which can be used to reduce the Mahalanobis score. We multiply this by a scalar hyperparameter epsilon to get a perturbed image. And it's been seen empirically that the rate of change of Mahalanobis score for a perturbed image is greater for an ID image than an OD image. So this can improve the separability between the two. And we see that applying fast gradient sign method on the multi-branch Mahalanobis, we get a further improvement in the AUC. However, again, we've got that parameter epsilon, which needs to be optimized on an external OD dataset. And so therefore, we're going to highlight this method to represent that this is going to be an optimized score. Quickly running through our unseen sex task, we can reconfirm the trends we saw with the pacemaker task. But I want to highlight here that looking at the third branch, that has a better AUC than the fourth branch in this method, which again highlights the benefit of using multiple detectors for Mahalanobis score. These trends were also reconfirmed on a VGG model, which I'm not going to go through today, but please check out our paper if you're interested. So we've seen that multi-detector systems can improve the Ausch distribution detection performance. However, can they actually be used in a real-world deployment? What I mean by this is in a single detector system, we develop a scoring function where we only have to find a single threshold for separating ID and OD inputs. However, for a multi-detector system, we now have many scoring functions, and this creates an additional challenge of trying to find multiple thresholds for each detector, which are all complementary to each other. So to demonstrate that it's feasible to find these thresholds, we applied a grid search on the 4 detectors on multi-branch Mahalanobis for resonant 18. We then configured these thresholds such that if one flags an input as OD, it's then marked as such. These thresholds were then optimized using the balanced accuracy metric over the whole of the real dataset, so that includes the unseen sex task and the unseen pacemaker task. Comparing this to the best performing single detector systems from our previous analysis on resonant 18, we see that a theoretically attainable upper bound for multi-branch Mahalanobis can outperform both the optimized single layer or the weighted combination techniques. This shows that thresholds can be found to accommodate multi-detector OD tasks, and this inspires future work for trying to configure multi-detector systems. So, to summarize the key takeaways of this talk, where you apply Mahalanobis distance matters. Applying it on the last in layer of the network can be very suboptimal, despite being the most common practice in previous works. Moreover, we saw that measuring Mahalanobis score after a ReLU operation generally improves the Ausch distribution detection. We also saw that different OD patterns are optimally detectable at different depths of the network. There's no single layer or combination of layers that can optimally detect all patterns. We also saw that the sum of distances from different layers can outperform the best single layer in some cases. And this work motivates future work on designing and calibrating multi-detector Ausch distribution detection systems. So thank you very much for listening. If you found this talk interesting and are interested in work in Ausch distribution detection, I encourage you to please follow on social media provided below. So hello and welcome